let's go back to the assembly of the global find M matrix for a diffusion problem in 2D. It's really in 2D. And let's see what happens with the transformation of the geometry and the transformation of the gradients to the reference domain. We'll prepare, hold strong, and be tough, because it's gonna be funny. Okay, what we need to discretize is something like that. And we remind that U is the J, Uj phi J at psi eta. The shape functions are defined in the reference domain. What we will be integrating really is, we already know that this integral needs to go over the whole domain, but once calculating the local matrices, we will be always calculating the local matrices over the domain of just the particular element, and then we will be assembling all the contributions from all the elements. So it's how we cover calculating over the whole domain. So we need to calculate that. And this one is obviously expressed in the physical domain. So these are gradients with respect to x and y, not with respect to psi and eta. We need to move it to the reference domain because our shape functions are defined with respect to psi and eta. So to say, we can write it's the gradient with respect to xy, and we want to calculate in the reference domain, but still the gradients must be with respect to x and y. U V Jacobian. And now let's write it. What's the gradient of U? The gradient of U is nothing else. It's du dx du dy. That's what we want to calculate, but all our discretization is expressed by functions depending on psi and eta. So we need to use the chain rule to write, okay, so this one is du with respect to dxi, dxi with respect to dx, plus du with respect to deta, deta with respect to dx. What's the second component? The second component is du with respect to dxi, dxi with respect to dy, plus du with respect to deta, deta with respect to dy. Well, gradient of V, I will not repeat that. Well, but now the funny part is we need to calculate gradient of U times gradient of V, because that's what we want to integrate. Yeah? Well, now, what does it mean? It means taking this one, multiply by the first component of that, two terms multiplication, already 4 terms, well, dot product, plus these 2 terms multiplied by these 2 terms of the V, so plus 4 terms, which makes altogether 8 terms. I did go through the derivation. I don't think it's particularly interesting to just be multiplying all these Xi, eta, etc. So let me just write the final result that we would arrive at. And this one is, you see, if you multiply these terms, you will always have 4 different terms. du with respect to d psi, derivative with respect to d eta, and you will have then, here it's repeated, so then you also have dv with respect to d psi and dv with respect to d eta. Here in this term they also repeat. So finally we would arrive at du d psi times dv d psi. If you make all this order with all these things, then you have d psi with respect to dx times d psi with respect to dx plus d psi with respect to dy times d psi with respect to dy plus du with respect to d psi, dv with respect to d eta, all the possible combinations, d psi with respect to dx times d eta with respect to dx plus d psi with respect to dy times d eta with respect to dy plus du with respect to d eta times dv with respect to d psi, d eta with respect to dx times d psi with respect to dx plus d eta with respect to dy times d psi with respect to dy, and that's the last line, du with respect to d eta times dv with respect to d eta, d eta with respect to dx, d eta with respect to dx plus d eta with respect to dy times d eta with respect to dy. Good. Yeah, your question.
So is it possible to gather all of those terms in some kind of matrix form?
I think not so much.
But okay, so maybe if we start with just describing the gradients.
I mean, yeah. Yeah, sure.
Times much.
Yeah, you could, but I think it's not convenient for what you want to achieve with that. You could. I will show you this in a minute. I mean, I will not write in the matrix notation, but what I mean is, okay, let's move back to what we are aiming at. We are aiming at calculating such an integral, keeping in mind that, and I don't want, we're keeping in mind that actually each u is what? Is sum of all j's, so phi j. And these test functions are like, sorry for that, like these are like phi I. And that's good because, to be honest, adding this sum would obscure our derivation even more. So I didn't want to do that. But the sum doesn't actually cause any problems because, like, see, you've got differentiation sum below the differentiation in front of that. It's fine. It's linear with respect to u. So it's really no problem to make the whole derivation once again, keeping the sum here if you wish. because then it splits into like this, you know, in front of that you've got some, you don't have U, you've got like phi j, phi I, okay? And you've got everything multiplied by Jacobian times the unknown coefficient. It's like what you want to get, but I don't want to obscure it right now. The idea with the, I've just lost my notes, sorry. Good. Now you need to substitute that to arrive at expressing everything by phi j and phi I. Just have a look that you only have, it's like the first variable differentiated with respect to the first variable, like the common abbreviation that at least I was using. It's like we call it lambda 1,1. This one is first, okay. So again, it's lambda 1,1. This one will be first, well, second, lambda 1,2, etc. And you've got only, well, you can only have 4 different combinations. So if you, let me just write it. The psi with respect to dx, I would call lambda 1,1. The psi with respect to dy, I would call lambda 1,2. The eta with respect to d psi is lambda 2,1. And the eta with respect to dy is lambda 2,2. What's the nice thing about that? Lambda 1,1, lambda 1,2, lambda 2,1, lambda 2,2. Just see, these are the elements of the Jacobi matrix of the transformation, not the usual one that we had from psi eta. So from the reference element, you want to map with some f, you need to map to the physical space. And then, what kind of Jacobian do you have? You've got dx with respect to d psi, dx with respect to d eta, dy with respect to d psi, dy with respect to d eta. Is the Jacobian of your usual transformation? Here you are using the determinant of the Jacobi matrix, and here you've got the Jacobi matrix of the transformation from the physical space to the reference space. And like in general, it's not easy because for nonlinear elements you have nonlinear relation. You don't have an easy way to find psi eta that is associated with specific x and y. That's difficult, and you don't want to do this. But what you know is that Jacobi matrix of the inverse transformation is the inverse of the matrix of the Jacobi matrix of the original transformation. So you do what is easy for you. You use the geometrical transformation from the reference element to the physical element. It's easy to be done. You calculate the Jacobi matrix. Then you calculate the inverse of the Jacobi matrix, which is easy because it's like 2 by 2 or 3 by 3 in the 3-dimensional case. And you've got the inverse, and you just need to identify, okay, this element is my lambda 1,1. This element is my lambda 1,2, etc. And there's an easy way to calculate these lambdas for each point in your element, and you only need to calculate where. Where do you need to calculate these elements? How will you integrate that?
In the quadrature points.
Exactly. You will be using the Gaussian integration to calculate the integral. So, and the Gaussian integration requires you to multiply some weight times the function value at the quadrature point. So you only need to calculate, and the quadrature points are defined in the reference element. So you know for which psi and eta you need to calculate the function value. So you have, because you know the shape functions and you know then it's easy for you to calculate the geometry transformation for a particular psi eta pair. Well, then you calculate the inverse of the matrix, and you can integrate something like that. Maybe I did it a bit wrong. Like then for matrix calculation, you would have everywhere here like I, J, phi I, J, phi I, phi J, phi I. Now, yeah, okay, and you would have here just the summation for J, and then, well, if you integrate got the Jacobian times uj, and if you want to do, it's for the integration, so if you want to do the Gaussian integration, you would add Jacobian times the weight, then you need to add one more sum coming from the from the Gaussian integration, but let's not introduce the Gaussian integration right now. Here, you already see that you got a formula with two indices, I and j. And this is how you construct each element of the diffusion matrix. It involves all these terms from the geometry transformation. Well, and that's it. If you want to assemble the global matrix, what's the procedure? Do you remember from our 1D example? How would you assemble the global matrix for such a mesh?
Nodes coordinates.
Hmm?
Nodes coordinates first.
Mm-hmm. But what kind of first loop do you use? What do you loop over?
Elements.
Yeah, exactly. So you would loop over elements. Once you've picked some element, let it be this one. Let's say it's the first element, the mesh. What you need to do is you know its local nodes. So you know the shape functions. You can easily calculate that because I hope you remember that you use like xj times phi j is your geometrical transformation. So you're using the shape functions and the coordinates of the local nodes in the physical space to calculate that. So you can differentiate that with respect to psi eta. Then you arrive at the Jacobi matrix. Then you calculate the inverse of the Jacobi matrix. So you got all these lambdas. Like these derivatives are no problem because these are derivatives of the shape or test functions with respect to their natural arguments. So you can calculate everything like that. And well, you need to do it probably for like maybe 3 Gaussian integration points. So you need to evaluate each of them with some respective weight, and that's your ij coefficient in the diffusion matrix. And this sum is responsible for like local matrix multiplication with local unknown vector. Tim, question?
How do we calculate the lambdas?
The lambdas?
Yeah. We have to project each time, or?
No. See, what you need to do is, if you're in the Gaussian integration and you want to calculate, let's say, f at x d omega, then what Gaussian integration requires from you is like taking some weight wk f at x k, well, maybe times Jacobian if you do the transformation. So basically it requires you to calculate at some well-chosen points. Psi if we do the transformation, okay? So you know where you need to compute that. Now, see, how do you map the reference element from psi eta to such one? You use the coordinates of the first local node, second local node, third local node, times the first, second, and third shape function. Is clear? No.
The last sentence I didn't.
Okay. Okay. Imagine if you want to represent temperature field, you represent let's assume that's temperature. You represent temperature by taking temperature values in the nodes times their associated shape functions. And it spans you like, for example, the linear interpolation. Okay, so what's the difference between temperature and x coordinate field? If you just take one component, there is no difference. It's like also a scalar value field. Yeah? So you can use the same interpolation to calculate x coordinates everywhere inside the triangle. You can use the same coordinates, you can use the same interpolation to calculate the y. What would you have? Like phi 1, phi 2, phi 3, phi 1, phi 2, phi 3. Okay, no, in the matrix notation you need to do it differently. But this one will be correct. Phi 1, phi 2, phi 3 times x1, x2, x3. If you use that, and these functions are expressed with respect to psi and eta, yeah, then it's easy to differentiate this linear interpolation of x with respect to psi, and eta. Can you see that? Each of these functions depends on psi and eta. You can evaluate these functions for a particular psi, eta, that's not a problem. But now, really, analytically, you can differentiate, like dx with respect to d psi. What does it mean? It means d phi 1 with respect to d psi, d phi 2 with respect to d psi, d phi 3 with respect to psi, well, and the same vector. Okay? And because you know the explicit formula for shape functions, you can calculate it on the sheet of paper. For, with respect to eta, you do the same way. For y coordinate, it would be the same. So you got no problem to calculate this matrix. And it's your original transformation from the reference element to the physical element. Then we know that lambdas represent the elements of the Jacobian matrix of the transformation from the physical space to the reference element. So you know that once you've calculated that, you only calculate the matrix inverse to get that. Okay? And to do the Gaussian integration, you then simply loop over like 3 quadrature points, taking the weight times the function, and the function is then that, but you can already calculate that. 3 quadrature points add together, you've got the ijth element of the diffusion matrix. Questions? Okay, let's finish that. So you loop over elements. Once you've chosen a particular element, you know what the local nodes are. You can calculate everything that is under the Gaussian integration. Then you come up with the local diffusion matrix, and we repeat the process that we have discussed very, very exactly in our 1D example, where you distribute the entries of the elements of the local diffusion matrix to contribute to the global matrix.